Cool. Well, welcome to the Austin Cassandra meetup, guys. I'm Nick. I've probably met most of you guys before, but for those that haven't met me, I'm the guy that sends emails on Meetup. So yeah, this is our February meetup. Just so you know, next week or next month, the meetup falls pretty much smack dab in the middle of South by, which means we're not having a meetup because that would be a giant pain. And we don't have a April meetup planned yet. The April meetup is on the 16th. So if anyone has anything they want to talk about, how you guys are using Cassandra, or if you have something specific you are dying to hear about, and maybe I can figure out a way to organize a talk on it, definitely let me know. Besides that, somebody emailed me and asked me to mention that May 10th, there's a big data job fair here at Capital Factory. So if anybody is interested in that, I can't remember the name of it, so I'm a terrible person, but if anybody's interested, let me know and I'll send you the link to that. But yeah, tonight we're going to hear about the upcoming Cassandra 3.0 from Jonathan Ellis, the co-founder of DataStax and project chair of Apache Cassandra.
Thanks, Nick. I've got a bit of a cold tonight, so I apologize if my voice isn't projecting all the way to the back. There's some chairs up here in the middle. There's even some chairs down here in front if you dare get that close. But if you have trouble hearing, then by all means, feel free to move closer. So skipping the fluff here that I tell people Cassandra's awesome, you already know that. I like to start off by reviewing some of the features from earlier releases that I think are especially cool that people might have missed. Who's familiar with rapid read protection? All right. I love you guys. You're not just keeping your hands down to make me feel good, are you? Okay, so what rapid read protection is, in classic Cassandra, when the client goes and talks to Cassandra and says, hey, give me this row that I'm interested in, it's allowed to talk to any node in the cluster, which may or may not own the row being requested. And the node that the client talks to is called the coordinator. So the coordinator will relay that request to a replica that owns the data. And so we'll track in the cluster which nodes are, or which replicas are busiest. So in this case, I have 3 replicas, and I know through what we call the dynamic snitch that this replica in the green here is less busy than the others. He's responding faster. I'm not actually tracking busyness. What I'm tracking is response times. So I know he's responding fastest. So I'll go in and ask him for the data. But if he then falls over after I've sent that request, then in earlier versions of Cassandra, we'll just send a timeout to the client and say, sorry, I tried to get it for you. I didn't get an answer back. I don't know what happened. Maybe there's a GC pause. Maybe there's a network problem. Maybe the node had a power outage, but I didn't get an answer back. So I'm going to give you a timeout, and you can decide whether you want to retry or serve an error up to your user. And that's okay as far as it goes. The problem is that there's a window in time during which that node could be failed, and we're still sending a request because we don't know it's failed yet. So that's our failure detection window. And that takes 5 to 10 seconds on a typical cluster. So we want to avoid that. We want to avoid that period where we're sending requests to a replica that can't actually respond to us and giving timeouts to the users. So what we do, starting in 2.0 actually, we've been doing this for a little while now, we'll go to another replica first. And we'll say, we'll take the slowest 1% of our queries by default and retry those to another replica. And be able to serve that up to the client without timing out in the middle. So what that looks like, this is a cluster. This is a 4-node cluster, and halfway through this test, I shoot one of the nodes and kill it. And so you can see that there's that approximately 10-second gap where nothing is happening. I'm sending those requests to the replica, but it's not giving anything back. And so it waits for those to time out and waits for the failure detector to kick in and realize that the node's dead, and then it reroutes to other replicas. With the rapid read protection, this is what it looks like now. So there's still a dip because I have a quarter of my requests that I need to retry and send to another machine, and that's happening, under the covers, invisible to the client. But the larger my cluster is, the smaller that dip gets in comparison, because it gets spread out across more vnodes, more machines. So this is a latency graph from a production Cassandra cluster. And down here is the median request time, and up here it's the 99th percentile request time. So our median request time is about 800 microseconds. The 99th percentile is about 1.3 milliseconds. So we're keeping the slowest 1% of the queries, still within a reasonable factor of the average query time. So this rapid read protection really helps, besides prevent that outage when a node falls over. By doing those extra requests on the slowest 1%, we can bring down that 99th percentile response time. With Cassandra 2.1, one of our focuses was improving performance for native CQL queries. So here's what that looks like. Down here at the bottom, we have 2.0 for thrift queries, then followed by 2.1 for thrift queries. So barely budged. Thrift imposes constraints on us that there's only so much we can do to optimize those. In green, we have 2.0 for CQL queries, and in orange, we have 2.1. So we've been able to take the CQL performance and improve it by almost 100% for this best case scenario. So I say it's a best case scenario because this is a 100% in-memory workload. Obviously, I'm not hitting disk if I'm serving almost 200,000 requests per second for it. So we've gone on the record saying, who's got an application on thrift? Do I need to beat the thrift horse to death a little more? So we've gone on record saying we're not going to take your thrift away from you. Applications that are running on thrift are going to continue to work, but we do have a carrot that's if rather than throwing hardware at your performance, upgrading to CQL can be a reasonable approach as well. And it doesn't have to be an all or nothing thing, right? You can gradually roll out new features on top of CQL in an application that's still doing a lot of stuff based on thrift. So this is for, I said this earlier graph was a best case scenario. Here's a worst case scenario. So in this scenario, I don't have, or rather I barely have enough memory to cache my hot data set. So the rows that are being accessed over and over, I have enough memory for that, so I'm getting decent performance, but I don't have any extra memory. I don't have enough memory to hold the cold data set. And so what happens is, right here, a compaction is happening. And so in older versions of Cassandra, that would be really bad news, that would tank our performance, that the compaction was ongoing. And we've addressed that pretty well now. So there's a little bit of spikiness, but by and large, it's fairly stable, our performance during the compaction. But what happens where we fall off the cliff here is when the compaction finishes. And now we go from serving reads from those SS tables that are hot in memory, and now we're serving them from the cold ones. And that's why our performance goes through the floor, because those cold ones are not in the page cache. And so gradually, as we pull those in, the performance ramps up until we're good again. So this is on spinning disk because I wanted to make it dramatic at the impact there. But you do see a similar impact on solid state disk, but it's much smaller, of course, as as you have that better random read performance. So with 2.1, what we do now is we will start sending reads to those new SS tables that we're creating during the compaction process, and that avoids that all or nothing approach. So as soon as I've got 64 kilobytes worth of data in the new SS table, I can start serving reads from that, and then the next 64K I'll start serving reads from that as well. So there's no big all at once the dam broken and there's a flood of requests hitting the disk and bottling up. Now, writes, we have a similar story to what we looked at on the first slide, and so we've got Thrift 2.0, Thrift 2.1, CQL 2.0, CQL 2.1. But the difference is that we've got a lot more spikes where the performance slows down briefly. And what's going on there is we're actually maxing out the commit log disk. So this is an Amazon VM with 32 cores and 2 solid state disks, and we're maxing out the commit log disk. So what we've done in 3.0, one of the improvements we've made in 3.0 already is to add commit log compression. And so we're able to get more out of that commit log bandwidth that we have on that single commit log disk. We also have in the works spreading the commit log across multiple disks, which may or may not land in 3.0. It may land in 3.1. And then finally, a new feature that we backported all the way back to 2.0 is date-tiered compaction strategy. So this landed just a couple months ago, but we've backported it to 2.0 so people can test it out, see how it works. So it causes absolutely no changes in the rest of Cassandra. So you've got your level compaction strategy, your size-tiered compaction strategy. You can try out date-tiered compaction strategy. If it doesn't work, switch it back, and everything will go back to being exactly the same as it was. So there's no downside to trying it out, except that if you're going from leveled to date-tiered, then you're going to lose your leveling information. So that's just something to be careful of. But especially if you're doing size-tiered, there's really no reason not to try it out. So what this is it's a compaction strategy that's specifically designed for time series data. And we're trying to take advantage of some of the properties of time series data, one of which is once I insert a data point, it doesn't change. And another is I'm inserting my data in mostly chronological order. And I say mostly because there's some tolerance for events that arrive out of order. Because even if your application is generating events exactly chronologically, there's going to be network hiccups, there's going to be temporary failures, and Cassandra does hinted handoff so that those events arrive slightly out of order, and that's okay. But they do need to arrive mostly in chronological order, and I'll explain what the tolerances of that mostly are in just a bit. So the way it works is as I'm sending in writes and I'm flushing out SS tables, since my events are arriving in mostly chronological order, I know that this SS table has events that are mostly newer than these other ones, and this one has events that are mostly newer than these earlier two. And I define a window in date-tiered compaction strategy called the base time window. And that says, how aggressive do you want me to be at compacting events that are, chronologically close together? And so what I'm going to do is, whenever I have more than my minimum number of SS tables within my base time window, I'm going to compact all of those SS tables together. So it's almost like it's doing a major compaction for this window that I've defined, just for that window. So I compact those together, and I continue flushing new SS tables as new events arrive. New SS table, new SS table. Then I'll keep compacting the SS tables within that base time window. So I'm oversimplifying here a little bit, right? Because I'm just showing new SS table compaction. But what really happens is, if I have a new SS table come in, in that same time window, I'll compact those two together. Then a third one comes. I'll compact that together with the first two. Fourth one, compact that together with the ones in the window, and so forth, right? So I'm oversimplifying here just a little bit for the sake of the diagram. And I keep doing that. And then when I get enough SS tables for the next size window, which is defined as my base time times my minimum compaction threshold, my SS table count. So this is the same threshold that you use to tune size tier compaction strategy, right? It's the number of SS tables that are close to the same size in size tier compaction strategy. In date tier compaction, it's the number of SS tables within the same window. So when I get to that next threshold, I'll compact those together as well in another semi-major compaction event. And we keep doing that until we get to, I thought I had the number here. I guess I left it out, I'm sorry. But there's a second setting that says it's the maximum date tiering threshold. So we'll keep compacting these together, but there's a point at which if events are older than my maximum threshold, which is a day by default, I'm not going to compact them anymore. So I'll go up, I'll start with my base window, I'll multiply it by my minimum threshold for the next window, I'll multiply it again for the next window, and I'll keep multiplying that out until I get to a day's worth of data. And then I'm not going to compact anything that's older than that. So when I said it's okay for events to arrive out of order, that's kind of your maximum grace period there, is that threshold after which we don't compact anything anymore. So if you have events come in out of order after that threshold, everything still works, but now my queries that I expected to scan a single partition are going to have to hit other SS tables because they weren't compacted together. So you can actually check and see if your application is conforming to the date tier compaction strategy expectations by looking at the statistics on number of SS tables per read. And it should be really close to your minimum threshold. If it's more than that, then that probably means that you have out of order writes or possibly data points being updated after they were inserted, which is another way of saying out of order writes.
So how problematic is it for the stragglers, like the meter reads that come in days later off of some other system, to wind up way in a different SS table?
You're pretty close to having no compaction strategy at all in that scenario, because they're going to come in, they're going to be flushed, and then, if they're all coming in at once, then they'll just be flushed to SS tables and they won't be compacted. If they're coming in intermixed with other events that are in real time, then all hell breaks loose and you lose.
Is there any rule of thumb for what percentage of things should be all together, or what percentage of things it's okay to get out of order, where this still is obviously the dominant strategy for time series?
I think that's going to depend on how read heavy your workload is, right? Because the compaction strategy is there to optimize reads. And so if you're doing less reads, then it's going to be more forgiving to having those data points in other SS tables. Yes?
What if your reads are focused on recent writes more so than historical writes?
You're still in pretty good shape, because you've got that window that says, I want to be doing effectively a major compaction across the most recent writes. So it's actually very aggressive at compacting those. So basically our goal was to give you the best of both worlds for data that matches the appropriate workload, where you had size tier compaction that's good at write-dominated workloads, and we had level compaction that's good at read-dominated workloads, but we had trouble with workloads that did a lot of writes and a lot of reads. Date-tiered compaction solves that problem, at least for this scenario. So, like I said, we did backport it to 2.0 starting in 2.0.11, and in 2.1.1 it's also available. If you're running who's running 2.1? All right. Well, if you're thinking about trying 2.1 out, 2.1.3 was released this week. So, that's it's worth trying out. I'll put it that way. One thing to understand about date time compaction strategy, it is pretty sensitive to the base window that you define. Our initial implementation set it to 1 hour. Now it's, I believe it's 5 minutes now. It may even be 1 minute. Do you remember, Tyler? Yeah, I think it's 5 minutes now, but I don't remember what version that got committed in. So check that out when you try it out. It optimizes queries that look like this, where I give you a time range, and it doesn't need to be an actual date time data type, but it needs to be, this could be an integer that I'm comparing on. It doesn't need to be an actual timestamp, but I need to give it a bounding range between X and Y. So in particular, you were asking about the most recent things. Intuitively, it seems like I ought to be able to say something like select order by time descending limit 10, right? And saying, give me the most recent ones. And that implicitly gives me a bounding of from now until I get the 10 most recent. But the query planner was not aware of this kind of query until 3.0. So we did backport the base compaction strategy to older versions, but doing this, making the query planner date-tiered compaction aware is more invasive, and so we're not going to be backporting that. So if you need to do that query, just be aware it's not going to be as optimized until 3.0.
It's 60 seconds in 2.0.12 and 2.1.3.
Okay, so it was 1 minute. Thank you. So some of the stuff we did in 2.1 to improve your data modeling life. So I'm giving a talk on 3.0. Nobody's on 2.1 yet, so this is actually a good time to sell you on time to check out 2.1. So we're all familiar with lightweight transactions. Yeah, I can say if not exists, or I can say if some column value equals an expected value on an update, and Cassandra will make sure only one of those gets applied. But we can do cooler stuff with that in 2.1. So we've introduced a concept called static columns. Who knows static columns? All right, so we'll cover them for the majority here. So static columns are, just like in a Java class, if I have a static field, it's shared across all the instances of that class. In a Cassandra table, a static column is shared across all the rows in a partition. So in this case, I have a table of bills. My partition key is the user ID. And so the balance is going to be shared across all the rows for that user. So what I can do is I can actually have a lightweight transaction that spans multiple operations within a batch. But all the operations still have to be in a single partition. So lightweight transactions, you can use them in a batch as long as those are in a single partition. That's the rule. It will reject attempts to do a lightweight transaction across multiple partitions. So in this case, what I'm going to do is I'm going to say, update the balance, reduce the balance by 200, is what that first line is saying, if nobody else has updated it since I checked the balance last. So I expect the balance to be 84. I'm going to set it to 200 less than it was. And at the same time, in that same transaction, I'm going to insert a bill saying this is why I had that $200 bill. This is why you're overdrafted now. Another example. We had a customer whose application requirement was they needed to have multiple producers inserting events into a table and multiple consumers reading those events. But if a producer ever inserted an event older than the most recently consumed events or most recently observed event, then everything broke catastrophically in their application. So they used lightweight transactions to solve this by creating an event table that looks like this, where you have a sequence integer, and we initialize that sequence to 0 when we're starting a new event log, and then to insert a new event, we update the sequence, we increment it at the same time as we insert the event. So that makes sure that we're always increasing that sequence by 1, and there's no opportunity for events to be generated out of order.
That only applicable to static column?
Which part?
Well, sequence was static in the last slide, so does this only apply to static column?
You can do multiple updates and inserts within a partition and within a lightweight transaction. The static column doesn't have to be involved, but they tend to be less interesting. So the static kind of gives me some global state to manage those transactions with and manage concurrency with. So that's why I've got 2 examples with that and no examples without it. But sure, yeah, you're definitely allowed to combine those operations without a static column involved. User-defined types landed in 2.1, and what that looks like is we're basically creating a record or a struct that combines multiple primitive columns into a more complex one. So I can create an address type with some text and integer fields and a collection, and then I can use that in my users table with this addresses column defined as a map of text keys to address values. So one thing to note here is that I've added this frozen keyword here. That says that the address will be written out as a blob. So I can't just go in and say, update users set addresses home dot street equals something. I can't do that. I have to set the entire address to a new value. That's required in 2.1 because we're thinking in terms of forward compatibility. For 3.0, that's not required. And that's the default, is not being frozen. We think that's what more people are going to want ultimately. But so that the behavior of your application doesn't change suddenly when you upgrade from 2.1 to 3.0, the frozen keyword is mandatory in 2.1. So that's what's going on with that. Nested collections landed in 2.1.3, which again was released this week. So similarly, you're allowed to nest collections now as long as they're frozen. Collection indexing is here. So in this example, I have a songs table. I have a set of tags associated with that. I've created an index on those tags. and then I can say select where tags contains blues. So we introduced a new keyword here as well, the contains keyword. So we could have done it with the in keyword and reversed that, where blues in tags. And we did it this way around because of maps, because a map has both keys and values. And so you can ask where map contains, and that's going to look at the values, or you can say where map contains keys, and then that's going to look at the keys. On the operational side, 2.0 was the last version of bad counters. And by bad counters, I mean specifically that counters were not idempotent within a node. So is that big enough that you guys can read it in the back? Basically what happens in 2.0 and earlier versions, when I increment a counter, I write the increment to the commit log. So here's my first state of the counter. I've incremented it by 1. The counter value is 1. The commit log value is also 1. I increment by 1 again. Now the counter value is 2, but I've appended another 1 to the commit log, and so forth. I just append the increment to the commit log. And the reason we designed it this way is that this preserves the Cassandra property of a write never has to touch the disk to see what an existing value was. So this just lets us append those writes to the commit log as fast as they come in, and then reconcile them asynchronously. The problem is that this leaves us a window for corruption. So if I've appended those values to the commit log, and then I flush them, and I have a power failure at just the right time where the data is flushed on disk, but I haven't marked the commit log as flushed yet, which are 2 separate operations, there's no way to make that atomic, then when I restart Cassandra, it's going to replay that commit log and increment those values again. So I'm going to double count some of those values. So there's a pick your poison where I can either mark the commit log first and then flush, or I can flush and then mark the commit log. And we went with that second one, but either way, you're going to get, either you're not going to count values at all, or you're going to double count under the right scenario. So, so there's no way around that with this design. So for 2.1, we said, okay, now there's no way around it. We're going to need to have to check the existing counter value on an update so that we can write the entire merged counter value to the commit log and not have this corruption problem, because corruption is worse than slow performance. If we can only get 1, we're going to go with giving you the right value, giving you the right answer. So now when you insert the increment by 1, I'm writing 2 to the commit log, that's the full value of the counter. I decrement by 2, I write 0 to the commit log, that's the full value. Replaying the commit log is now completely safe. But we didn't want to give up performance, because that's a crappy story to tell people, is that, oh yeah, counters will never corrupt your data, but oh yeah, the performance got a lot worse. So we put a lot of effort into keeping the performance high. And so the approach we did was, we have internally what we call a counter cache. And we basically promote hot counters into basically an atomic long internally, so that those become very fast, even though I do have to check that existing value on the increment. I'm not having to hit disk every time. So here's 2.0 in blue, 2.1 in orange for counter increments. So I'm pushing about 45,000 operations per second on this machine for both 2.0 and 2.1, but 2.1 is a lot more consistent. And that's because doing that merge on update and having that cache of hot counters means that I'm doing a lot less memory allocation. So I'm doing a lot less garbage collection, and there's a lot less variance in performance because of that. So note the scale here. So we've gone from 45,000 for the low contention scenario. Low contention means most of my updates are spread across lots of partitions. So this is the recommended way to use counters, because if you have lots of updates to the same partition, there's going to be contention. And that's true whether you're in 2.0 or 2.1. Both of the designs suffer when there's a lot of contention in a partition, yeah.
So there's contention even if you're updating counters in separate rows within a single partition. Like there's a partition, a whole lock of some sort.
Right. Mm-hmm. That's my understanding.
Okay.
We've gone from 45,000 to 7,000 for 2.1 in a high contention scenario, and 5,000 for 2.0. So 2.1 is 50% faster, but that's still a factor of 7 slower than the low contention scenario. So we definitely recommend continuing to design to avoid that contention. But if you can't, then at least we've made it a little better in 2.1, and that's because of the counter cache is why that we've taken out a little bit of the steam. Finally, in 2.1, we've introduced what we're calling incremental repair. So the way repair works, as you know, we scan our data set, we build a tree of hashes, we exchange the hashes across the replicas. The replicas compare the trees and say, well, if the top of the tree is the same, then the data that created that hash is also the same, so we're good. If the top of the tree is different, we'll check the left child, we'll check the right child, and drill down until we figure out what block is different, and then we'll transfer that block across the network. So it's very network efficient because we just have to exchange trees, and then we exchange the data that's out of sync. But what's not efficient is building the tree. That's what's painful, because we have to scan the entire data set, and if my data set grows 25% bigger, then I need to scan 25% more data to do my repair. So as my data set grows, my repairs get slower, because even if all the data is perfectly in sync, my repairs still get slower because of the cost of building the tree. So what we'd like to do is take advantage of the fact that once our SS tables are written to disk, they're immutable. We never change them again. We write out new SS tables with new updates. So in theory, once I've repaired an SS table, I should never have to repair it again. So that's the approach that we take for incremental repair. There's some implementation details that make it tricky. In particular, we need to be careful once we've repaired SS tables that we don't mix them with unrepaired data during compaction, because if we mix it with unrepaired data, we've contaminated it and we have to repair the whole thing again. But conceptually, it's a simple approach to minimize the amount of work that repair has to do. So if you're going to migrate to incremental repairs, the default in 2.1 is still to do traditional, I build a tree of everything repair. And that's mostly because we took a, we don't want to surprise people, especially because of the ramifications that I'm going to talk about right here. So we want the principle of least surprise, and then when you go and read the upgrade notes and say, oh, I should try out this incremental repair, then you can do that and opt into it knowing what you're doing. So the way that you opt into it correctly is by first running upgrade SS tables to get everyone on the 2.1 SS table format, because 2.0 doesn't have room in the format for that repaired flag. And then we'll mark those SS tables repaired, and then run a full traditional repair. And the reason we do it in this order is while the repair is running, we're going to have SS tables being flushed. And those SS tables aren't necessarily going to be part of the repair. So if we run repair and then we mark them repaired, we could mark SS tables that were flushed after the repair started and weren't actually repaired. So we mark repaired first, then we run the repair, which is slightly counterintuitive, but that's what you got to do for it to be maximally correct. Once that's done, then you can start doing the incremental repairs. So what you need to know, though, is if you don't do this and you just jump into doing the incremental repairs, then level compaction in particular is going to get confused. Because I said that we need to be careful not to compact unrepaired data with repaired data. And so when I do a repair, I'm not necessarily repairing all the data on the replica all at once. I can be repairing pieces of a token range. And so if I repair part of the data on my replica, and then I said, okay, you're the repaired data. You're going to go live in the repaired arena for compaction. I've got this other data that got leveled. It was originally leveled, but now it's all put into the unrepaired ghetto. I'm going to have bad performance until I re-level that. So it's not super bright about taking advantage or recognizing that leveled compaction has these special needs, which is why we recommend going into it after upgrading everyone to be flagged as repaired and avoiding that problem. Does that make sense? I hope I explained that reasonably well. Yeah.
Is there any sense to actually running an old repair after doing incremental ever? Like bit rot or something like that, or disk corruption? Or...
Yeah, the main reason is if I lose a disk or I have a disk go bad, then since I've marked those SS tables repaired, I'm not going to repair them again by design. So in that situation, then you would need to go back to an old, a full repair. What we'd actually recommend instead, since there's no way to tell Cassandra you've lost this, this specific partitions, it's going to continue to try to serve those up if you leave it running while that repair is going. And you'll be serving up stale data because it'll serve up whatever data it can actually read from the other disks. So we actually recommend in that scenario, kill the node and re-bootstrap it rather than doing a repair. But if you did want to take the repair approach, then you would need to do the full repair. All right, so last change for 2.1 is we introduced a feature that makes the row cache not suck. So everyone's first reaction when they start playing with Cassandra is, oh, hey, row cache, I like cache. I'm going to turn this on. And then their second reaction is, oh my God, why did my server fall over? Because the way the row cache works, of course, is it pulls in the entire partition and serves up reads from that cached partition. So if you have one 10 gigabyte partition, it's going to screw things over pretty bad. So what we've introduced in 2.1 is this directive here, rows per partition to cache. So it caps how much of that partition is going to be kept in memory. So even if you have a data set with wildly varying partition size, you're still safe. It's still going to prevent you from shooting yourself in the foot there. So the way that works is it caches the first rows, the rows at the beginning of the partition, in collation column order. So in this case, I have Nick and Mike. They both have a bunch of notifications coming in from their Friendster application. And so I've told it to cache the first 3 rows of each partition. So I'm going to cache the first 3 at the beginning of the Nick partition, the first 3 at the beginning of the Mike partition. So that's not tunable. It's always the beginning of the partition. So if that's not what you want, you can go back to the old row cache behavior by saying rows per partition to cache equals all. But for all the use cases we looked at, people were either caching the beginning of the partition or the end of the partition, and you can turn the end of the partition into the beginning just by reversing that collation order, Jeremy.
Right, I think it's nice because it rewards good modeling behavior, because if you have time series data or whatever, doing it at the beginning makes more sense. You're not scanning within the partition, and so it's nice because it rewards you for doing something that's going to be more performant for you anyway. So even if you didn't have row cache, going to the beginning of the partition is more efficient, and so this will be more efficient. Plus, you have cache at that area. So.
That's true. And then we also introduced kind of an extended beta for Windows support in 2.1. So if you were saying, I really want to run Cassandra, but I can't until I can run it on Windows, then now you can try it out. We're not promising production readiness until 3.0. That's what we're targeting. But we've killed the obvious problems. And so, if that's something you're interested in, then we'd encourage you to try it out and let us know how it goes. So 3.0, 45 minutes in, we hit 3.0. It won't be another 45 minutes. This will actually be pretty quick. We're moving to JBOD-aware vnodes, or vnode-aware JBOD, depending on which way around you want to think about it. But basically, right now, when I have a bunch of disks that I'm storing Cassandra data on, all my data for all my token ranges are, go to whatever disk is least busy or has the most free space, and we just kind of load balance across the disk like that. So I've color coded my vnodes for this replica, and so you can see they're just jumbled across all the disks. So what happens then if I lose a disk is that I lose data for basically all my vnodes, is what I can expect to lose. And so what we give you is we give you kind of two crappy choices. If a disk fails and we detect that, we can either shut down the node, which kind of sucks because now I've lost capacity for all those healthy disks as well, or I can keep going and try to serve up whatever data I have left, which is also kind of crappy because now I'm going to be serving up stale data. So the way people get around this is by deploying on RAID 10 and say, well, okay, we'll let hardware solve the problem, and that'll give me that room to re-replicate that disk in hardware instead of having to deal with this. But that's a crappy choice too, because if I've got 3 copies of my data across my cluster and now I've got RAID 10, I've actually got 6 copies, and that's kind of expensive. I'd rather, especially if I'm on SSD, which you should be, that's money that I'd rather use saving my data and not preparing for losing a disk. So in 3.0. we're pinning each vnode to a specific disk. So we'll typically have many more vnodes than disks. So I haven't captured that in this diagram, but basically we'll pin each vnode to a disk. So again, in the Cassandra assumption, I have lots more partitions than vnodes, and I have lots more vnodes than disks. Those are the 2 assumptions. So if you violate those assumptions, then you're going to have unbalanced behavior. But those are pretty good assumptions for most data models. So once I have this layout, then if I lose a disk now, I can tell the rest of the cluster, hey, I lost disk 4, which corresponds to vnodes X, Y, and Z. So now you can, don't bother sending me requests to those. Send those to other replicas instead, and I can repair that or whatever without having to worry about serving up bad information in the meantime.
Does it reroute X, Y, and Z back to one of the other two? Does it re-pin them for new data, or as it comes in? Or?
Right. Yeah.
Okay.
I'm waving my hands a little bit. This hasn't been committed yet, but that's how it should work.
Okay.
Yeah. So I mentioned user-defined types. They're frozen in 2.1. That's your only choice. 3.0, they become unfrozen by default, and that lets me update pieces of that UDT without having to update the whole thing and rewrite the whole thing. Another pain point on the operational side, I think repair was the biggest one, but the second biggest one is hints, and we're addressing that in 3.0. So we've used in since really like 0.5, but 1.0 is where we standardized on the schema we have now. We've stored hints in SS tables just like any other data that Cassandra stores, which is convenient because we have this log structured merge tree-based storage engine, so we might as well leverage it. The problem is that the trade-offs that SS tables make are not really optimized for hints. SS tables are designed to give me random access on reads, which we don't do with hints. They're designed to allow me to update pieces of a row, which we don't do with hints. So SS tables are overkill in a way that harms our performance. So what happens when we write a hint to an SS table is first we write it to the commit log, then it goes into the mem table, just like any other write. It goes into the mem table, eventually it's flushed to an SS table, but then we've actually kind of got double jeopardy because when we deliver the hint, we delete it. So we write a tombstone to the commit log in the mem table and flush it to an SS table. And then there's actually even more because we need to compact those SS tables to reclaim the space that the hints were taking. And basically what we do is we compact all the hints once we deliver to us, we complete a handoff to a given replica. So if I have multiple replicas that I've been generating hints for, then my write amplification goes through the roof because I'm rewriting all the hints that I haven't delivered yet when I do that compaction. So what we do in 3.0 is we basically just keep a file per peer, per node in the cluster that we have hints for, and we just append the hints to that. It's just serialized mutations. We just write those out. It's almost like another commit log. We just append those hints, and we do that on a per replica basis. So when we go and we are able to successfully replay the hints to a node that came back up, then we just delete the file. So it's almost free. Now in practice, there's a few. It's a little more sophisticated than that. We'll actually have multiple files of a few megabytes apiece, so that we can deal with replaying some hints successfully and not others. So if I had 100 gigabytes of hints for that guy, and I replay 10 gigabytes of them, and then he goes down again, I don't have to start all over again. So we introduce a little more granularity than one file per customer, but that's the idea. We're also introducing JSON support. So the idea here is not to give schemaless documents, because schemaless documents are a misfeature. We want Cassandra to know what data types to expect so that it can enforce those rules. So that when you have multiple teams using Cassandra as the source of truth, they know what to expect. And you don't have one team writing a user ID as an integer, another team writing a user ID as a UUID. Technically that's that could work, but it's not a good experience when you need to go in and say, how many users do I have? Because now I need to reconcile that at read time. So Cassandra will enforce that for you, even in the JSON world. So in the JSON world, what we do is we'll take the documents that you give us and map them to the Cassandra schema. So here's my address and users type and table from earlier. So here's a JSON document that has a map of addresses with a home address, and I can insert JSON into users, and Cassandra will map that to the existing schema. So it can map to user-defined types, it can map to nested collections. It's fairly flexible like that. It can even deal with data types that don't really exist in JSON. Like JSON only allows text keys in a map. And so if I have a Cassandra map that says I have integer keys, then we'll allow the insert JSON a statement to coerce those to the Cassandra data type, even though it's technically not actually JSON. Yes?
Is the schema mutated as new documents arrive that have fields the preceding documents didn't have?
No. If you want to change the schema, you need to alter table, you need to alter type.
So the first thing you send it needs to be complete comprehensive across the field space.
Right. So the way the way you do dynamic, fields in Cassandra is with a map, right? So if you have a if you have a travel business and you have thousands of hotels and some of them have different features, like I'm close to the sea and others don't care about that, you could have a map of those features and have it sparse in that respect. But yeah, the goal would be I'm not running alter table every time I do an insert. That should be a relatively rare occurrence.
So maybe for clarification, you have to set the schema before you do any JSON. So it's not about whether the first JSON insert is correct, it's about what you set the schema as in CQL. Does that make sense?
I see. So you can insert a JSON document, but you still have to describe the CQL schema.
Right. So here I'm using the schema that I've defined here, and then I give it a document that corresponds to that.
Okay.
Mm-hmm.
It's not schema.
Right. And then we're adding user-defined functions to 3.0. Basically, what you do is you give it the function name, the argument types, the language, and the body of the function. So if you remember triggers from 2.0 where you have to ship the jars around the cluster yourself, that's not how user-defined functions work. We'll compile them for you, we'll distribute them across the cluster, and manage, create, and execute permissions. So all of that is handled in a more user-friendly manner. So all you can do with user-defined functions in 3.0 is select them in the select clause, not in the where, not in the where clause, not anywhere else, just in the select clause. If you want more details on the implementation, Robert Stupp wrote the code, and he's got a presentation from Cassandra EU a couple months ago. So if you Google Robert Stupp user-defined functions, you'll come up to his presentation here. Super briefly though, here's a more complicated example because we allow you to define aggregate functions as well as simple scalar functions. So the way let's start at the bottom. The way an aggregate works is you say create aggregate, and then you give it a function that collects the state as it merges the rows together that are part of the aggregation, and then you give it a state type. That's what S-type stands for, is state type. That this is what I'm maintaining my state in between function invocations, and then a function to call against that accumulated state to get the final value. So as an example, we're going to look at a function that computes the average. So I'll create my state function is going to take a tuple of basically a long and an int, because if I'm doing an average, what I'm going to do is I'm going to sum all the values, and I'm going to count how many values there were, and then at the end, when I'm done, I'll divide the one by the other. So my state is going to be first the sum, and since I'm summing integers, my sum can be larger than an integer, so I use a big int, and then the count of the integers that I'm summing together. And then the second parameter is what am I aggregating together? I'm going to aggregate a new integer into my state. And so basically what I'm doing is I've got this tuple, so conceptually what I'm doing is I'm taking the part of the tuple that holds the sum and I'm adding the value into it, the part of the tuple that holds the count and I'm adding 1 to it, and that's what's going on here. So state is this Cassandra tuple object, and I'm set long, get long to pull those values out and put them back in to the mutated state. So then once I've aggregated those values together into this state, then I've got my final function to turn that into the actual average, and then all I do there is I take the first part of the state divided by the second part and return that. So the goal here is to be able to use these in what I'm going to call Cassandra type queries. So typically queries within a single partition that are going to touch a few dozen, maybe a few hundred rows. This isn't intended to be a replacement for Hadoop or for Spark. And this is for short queries that I'm running thousands of times per second. So that's still the goal, but this allows me to push that computation to the server rather than having to pull all those values client side and then compute it there. Yes.
So I'm guessing this runs in serial somehow. You don't have a parallel execution of these.
Yeah, we're not trying to do parallel execution of parts of the aggregate. Some aggregates don't parallelize nicely.
Yeah.
So we're not attempting that at this time.
So will the database be locked while it is executing?
Is the database what?
Locked? Like, will it freeze?
No, there's no locking. It's still an eventually consistent system. While I'm going over those, somebody could be changing them under me, and deal with it, right? Your alternative there would be to be doing lightweight transaction updates, and that's usually not worth the performance hit, but it is an option if that's what you require.
Okay. So who's doing the computation? Is it the coordinator or is it the query?
The coordinator does the computation because we need to reconcile the values from the different replicas, and then we can run the aggregate. So if we were doing consistency level 1, we could, in theory, push the computation to the replica. We haven't done that optimization just because we're not sure if it's worth it, if it's a common enough operation to be worth optimizing for. So yeah, right now it does the computation coordinator side.
What languages are supported?
So basically anything that speaks the Java scripting API, out of the box we give you Java and JavaScript, but if you want to go in and install a JRuby jar or whatever, then we can deal with that.
I think JRuby, Json, and Scala are probably the easiest ones to add support for. Pretty much
Just have to add
just add a jar to the lib folder.
class manage.
Yeah, I tested it out with Json, and I think Robert tested it out with JRuby and Scala, and they worked pretty well. We haven't done any benchmarks though to see how much slower or faster they are. So.
Now, one thing that's worth pointing out is that all these parameters are boxed, right? So I am saying i.int value because it's a Java integer with a capital I. It's not a primitive int. So just be aware that that's going to be going on. It's not really meant for super high performance computing. If it were, then we wouldn't be boxing everything. But it does let you push some of that computation to the server rather than pulling it over the network and doing it client side. In 3.1, we anticipate adding functional indexes. So we were thinking, maybe we can do it for 3.0. Doesn't look like it's going to happen in time, but that is on the table, that we want to be able to push those into the where clause as well as functional indexes. So I can do queries like this here on the bottom. So that is coming. Speaking of indexes, we do have a big change coming in 3.0 where we're introducing global indexes to go with the local indexes that we've had for years. So just as a refresher, when I create an index in 2.1 or earlier, I'm creating a local index, which means that each node is responsible for indexing the data that it owns. What the consequence of that is, if I go and I say, give me all the songs in the Rollaway album, then then I need to query each node in the cluster and say, hey, do you have any songs for this album? And then I pull those answers back together, and I can return it to the client. So it's not every node in the cluster, but it's one replica of each token range, multiplied by your consistency level. So potentially every node in the cluster, in practice, between every node and every node divided by your replication factor, depending on your consistency level. But the point is that as I scale my cluster, my index queries don't get faster because I'm querying proportionally more nodes. So that's why our best practice advice has always been, if this is a hot query, denormalize instead of indexing because of this property. If it's just a kind of an admin function that happens 100 times a day, who cares? Throw an index on it, call it a day. It's not gonna be a big deal. But if you're doing it 100,000 times per second, then you need to denormalize so you get that scaling property as you grow your cluster. So global indexes is basically going to do that denormalization for you. It's going to take all the data for a given index value and co-locate it in a single partition that gets replicated. So now when I say, give me all the data for Tres Hombres, all the songs in that album, I can just go to the node that owns that index partition and have my answer.
So that's like an easy way of getting new tables, or an easy way of, so it's like an entirely new column family.
You can think of it as a specialized materialized view, I guess, but it's certainly not a replacement for create table in the general sense, right?
That's what I'm asking. What's the difference when you get down to that?
The difference is that create index denormalizes exactly the information from this base table that I'm indexing and nothing else, right? So if you had some special computation that you needed to run along with that, no, I can't help you with that. But if all you care about is pulling out the data from the base table based on a predicate, then I can denormalize that for you automatically with the index. Any other questions? All right, thanks guys.
When is 3.0 expected to?
We expect 3.0 to drop in May. So about 3 months.
Would you recommend 2.0 users go through a 2.1 to 3.0 or directly to 3.0? What's the backwards compatibility for a major release?
We haven't yet targeted backwards compatibility across multiple major versions. So you will be expected to upgrade to 2.1 first. If you want to do a rolling upgrade. If you're willing to shut everything down and then restart the cluster on the new version, then it will be disk level compatible with 2.0. But network level compatibility is typically just one major release.
That might not be the case.
Might
Depending
not
on
be.
how we manage the schema, there might be a few cases where that doesn't work. So I would say in pretty much every case you should go to 2.1. Yeah. But
Optimistically, we're envisioning a world where 3.0 will be network compatible with 3.1 and 3.2, and then you won't be forced to upgrade until we hit the 4.x series. But right now, we're not making any promises for being able to skip 2.1.
Plus the upgrade from 2.1 is more QA, so it's a little bit more incentive too.
When does 2.1 become the stable release? You're sort of dropping hints that we should be expecting that sort of soon.
Test out 2.1.3 and let me know. Yeah, if it were me, I would probably be leery of 2.1.3 in production, so I would test it out and see how it goes. But I think we're getting close. I'm pretty optimistic for 2.1.4. So that's my best guess.
Okay.
All right, thanks guys.